Hello there, 8th graders. This is Mrs. Minowitz, and I'm here today to talk to you about the structure of the Earth and tectonic plates. So we're going to start by talking about the different layers of the Earth. And the layers of the Earth can be divided in different ways depending on what properties of the layers you're talking about. If you are talking about the composition or what it is made of, you are going to be using different layers than if you are talking about what are called the mechanical layers, and that is having to do with how solid or rigid they are or how they can move. So we're going to be using terms from both sides, okay? But I wanted to give you a diagram that shows how those words can be used differently, or if we're talking about one part, what it has to do with the other parts. Okay? So the structure of the Earth, okay? We're going to start from the outside and work our way in. The outest part that you are standing on is called the lithosphere. And this is another word for the tectonic plates, and we'll get to that in the second half of this video. But these are the outermost layer of the Earth, and there are different pieces of the lithosphere. This includes the crust and the upper mantle. So if you're looking at the diagram, okay, the lithosphere over here on the right, okay, takes up the crust and the upper mantle from the diagram on the left. The lithosphere is solid and rigid. It does not move easily. Lithosphere. This second layer is the asthenosphere. This is a softer layer. It is not as solid and rigid as the lithosphere. And this is where pieces of the lithosphere move on top of this. It's kind of like you have things floating on another part beneath it. Okay? So the asthenosphere is softer. It is underneath the lithosphere. The mantle is the middle layer, if we're talking about it compositionally. This is where convection currents are at, and this is what causes the tectonic plates to move. Convection, in case you don't remember that word, is the transfer of heat through a liquid or a gas. So one common example of convection is if you've ever watched like water or soup boiling, and you see things rising up, kind of sinking back down on the sides. That is an example of convection. Now, if we take a look at what is happening in the mantle, the middle layer here, we have rock that melts. Not necessarily like runny, like water, but it has melted and it is able to move. And when that happens, our rock kind of moves depending on what's happening there, and it creates these convection currents. So at the top of the mantle here, it is cooler than at the bottom. And when that happens, our rock starts to cool, our magma starts to cool. When it does, it gets more dense, and if something is more dense, it sinks. Now when it reaches towards the bottom, it's going to get warmed up because it's warmer there. And when that happens, it is going to become less dense and rise up. And we get this cycle moving over and over again, which creates these currents that are strong enough and able to move our different pieces of the lithosphere. Very, very slowly, but they're able to move those different pieces. This is what causes our different plates to run into each other, which is what we're going to talk about in the second half here. Structure of the Earth, finishing that up. The next layer as we move in is the outer core. The outer core is liquid, and then the inner core is solid. It is very, very dense. It has the weight of all the other layers on top of it, so that compresses everything together and makes it very dense. So tectonic plates, remember these are pieces of the lithosphere. Pieces of the lithosphere, and they move around on top of the mantle. And when they do, eventually they're going to either move towards each other or move away from each other. So they are what are called tectonic plate boundaries, where the edges of these plates are at, or these pieces are at. And there are three different types of boundaries that we're going to talk about that we kind of explored earlier in class. The first type of plate boundary is a convergent plate boundary. This is where tectonic plates push towards each other or together. They are moving right at each other. And when this happens, we see certain things. We will see subduction. So subduction is when one plate, our oceanic crust, goes and moves underneath our continental crust, and that creates an area of what's called subduction. When this happens, we also will see trenches and volcanoes. Those are associated with subduction. We will also see mountains And we will see mountains a lot when we have two continents moving towards each other. This is how Mount Everest was formed and continues to form, because there are two pieces of the crust that are moving towards each other. That is convergent. Second type of plate boundary is divergent. Divergent are when tectonic plates move apart. When this happens, we commonly see what's called seafloor spreading, which is where our ocean is literally spreading apart, and mid-ocean ridges. This is where new oceanic crust gets formed, is in the middle here, and we see those features when we have plates moving away from each other. The third type of plate boundary is called a transform plate boundary. This is where tectonic plates slide past each other horizontally, and this is where earthquakes commonly occur. And they occur there because we have it shifting along a fault line, and this creates our earthquakes. Now, if you look at your map, I'm going to talk about a couple different places and what happens there. First one is labeled as number 1, and this is between the African plate and the South American plate. And if you look up how these plates are moving, they're actually moving away from each other. So something that we would expect to see there is seafloor spreading and mid-ocean ridges. At location number 2, these plates are actually moving towards each other. When that happens, we will see subduction. We would expect to find volcanoes and trenches in that area. At number 3 over here, we again have plates moving towards each other. But when this happens, if you look at it up over here, we have two continents moving towards each other, and when that happens, we would expect to see mountains. Okay. We would expect to see mountains. So these are some examples of what can happen at different plate boundaries. Now, to get to this idea of seafloor spreading, we need to understand this idea of continental drift. So continental drift is this idea that continents can drift apart from one another and have done so in the past. And when this was first thought of and people started researching it, they thought people were kind of crazy for developing this. It was not considered like a good idea. People thought this guy was nuts. It was just proposed by Alfred Wegener in 1918, and when he did this, people were like, this guy's crazy. He's nuts. What he's saying can't make sense, because they didn't think that continents could move because they didn't really have experience with continents moving. There was some evidence that he had, though. He used evidence, points numbers 1 and 2, and then later number 3 was discovered. And the evidence behind the idea that the continents move is, one, the fit of the continents and how the continents all fit together. So the idea of Pangea and our continents all fitting together was one piece of evidence. You can kind of see how this works here, how they all fit together. And that gave the idea that, okay, the continents have moved. Another piece of evidence is if you compare fossil types across the oceans. If you put the continents together, the patterns of where their fossils are located makes a whole lot more sense than if they're separate. So that gives more evidence that at one point in time they were all together and could eventually move. What was not available was evidence for seafloor spreading when this idea of continental drift was first come up with. But eventually, okay, there was this concept of seafloor spreading that has been shown to be have evidence for. So basically, we get new oceanic crust is created at mid-ocean ridges, which is again at a divergent plate boundary. And what happens is that basically we have crust moving away from each other, and you have these lava coming up that cools, becomes more rock, and so you're creating new crust in the middle of the seafloor. My question for you, though, is if the seafloor is constantly spreading, why isn't the Earth getting any bigger? And if you stop and think about it, well, if it's adding somewhere, we have to be taking away somewhere. And the answer to that question is in a subduction zone. So in a subduction zone, we have crust moving beneath that would eventually melt and get recycled. So over time, all of the crust of the Earth, especially the ocean, is getting reused and recycled. We'll talk more about these concepts in class. Have a good day.